Welcome to today's video on labor supply and taxation. In this video, we consider a consumer solving the following maximization problem, where the consumer has to choose how much to consume and how much labor to supply. Consumption is good, that gives you utility. Labor supply is bad, that decreases your utility. What you can consume is whatever you got in resources, X, and your resources X is the sum of your cash in hand to begin with, the wage income you get from supplying labor, so that's the wage times labor supply, minus your taxes, where the taxes is a standard labor income tax, which just multiplied the total gross wage income, and then an extra tax, which is on all labor income above a cutoff kappa. So this is a top bracket labor income tax. Labor supply has to be between 0 and 1. Analytically, this is a bit irritating to solve this problem because of this maximum here, which implies that it's not differentiable. So it's a good sort of example of where it's easy to use a numerical solution instead. One thing we can realize about the problem is that because the utility is monotonically increasing in consumption, so that is you can always get more utility if you consume more, then you will always choose to consume all of your resources. So no matter your decision on labor supply, we know that your consumption supply is just to consume everything. The baseline parameters that we will be considering is that the initial resources or the labor, the cash in hand is 1. The disutility factor on labor supply is this new is 10. The epsilon here, which can also be called the fridge elasticity of labor supply, is 0.3. The standard labor income tax is 0.4. The top bracket income tax is 0.1. And the cutoff is 0.4. Now the questions in this is that you should construct a function which solves the consumer problem given these parameters. You should plot the optimal choice functions as functions of the wage in the range 0.5 to 1.5. Then you should consider a population with 10,000 individuals indexed by I, where you should assume that the distribution of wages is uniform such that the wage of the ith individual is drawn from a uniform distribution between 0.5 and 1.5. And we denote the optimal choices of each individual by L star I and C star I for the labor supply choice and the consumption choice. And then the final question is to calculate the total labor tax revenue by simply summing up over all individuals. So this is a good time for you to pause the video and try to provide a sketch on how you would solve these three problems. It will take some time for you if you actually wrote up the code, but it's a good idea to have a sketch on what are sort of the steps that you will have to take. Then you will sort of be better able to follow the way I suggest to do it if you have thought about that beforehand. So let's go to the solutions. So the solutions are in this notebook, and then they are in this labor supply model.py, this file, which will contain some functions that we will be loading. We will return to that in a minute. You can see that the file is over here in the editor, so it's readily available. I import NumPy and I import matplotlib with some settings, and I use the auto reload magic before I import the labor supply model as LSM. Because then if I made changes, then they're sort of updated when I run the notebook. So let's run this, and that's now done. Then I define all the parameters exactly as I wrote above, so there's nothing special in that. I just run this line. Then the first thing, sort of more technically, I need to do is I need to allocate some space for my solutions. So I know I will have 1,000 individuals, and I will just do a vector of the wages between 0.5 and 1.5 of these 1,000 individuals. And I've used this lint space function in NumPy, which exactly sort of return evenly spaced numbers over a specified interval. And then for the labor supply choice and the consumption choice, I will just use zeros in here. So let's run that. Now we're actually ready to find the solutions. So what I do is I loop over all the individuals, and then I call this find optimal labor supply function, which is in this LSM module, and that provides me with the solution for the labor supply. And given this, I also get an implied consumption choice. So I can actually just run this, and I have solved it. But now, of course, we need to understand this code. A good trick is you can always place your cursor on the function, and then you can press F12 to go to the function definition. So let's do that, and now it opens up. You can see that it opened up this file, and it went directly to this function here. It's always a good idea, I think, when you come to a function like this to understand sort of what does it do. And the first thing you can do sort of is look inside the function. It describes what the function is doing. That's very clearly stated from the name. And then it describes each of the parameters and telling you what does these parameters, what should these parameters be, what should these arguments be. And then it tells you, okay, what does it return? It returns the optimal labor supply. And then you can understand, so how is this done? You can see it's doing that by creating a lambda function, an objective, which is a function only of the labor supply, and it takes in minus the value of choice given this labor supply choice and the parameters. And then it's using from optimize, which is a module from SciPy. It's using the minimize scalar, which is a way to minimize a scalar function. So it takes this function now, which is only a function of the labor supply, and it optimizes, minimizes this. So that's why we have the negative in front here, and doing that within the bounds from 0 to 1, because I'm using the method called bounded here. So in that sense, it's easy to understand what this is doing, but there's two things that are hard here. One thing is, what is this value of choice function doing? We need to dig into that. And to some degree, it might also be hard to understand the minimize scalar, but you can take that as a black box to some degree. Now this is somebody else who has written that code, and that just works. And you can see once we get the result out from the optimizer, then we return the x value in the result, which is actually just the optimal labor supply. But once you sort of understand what's happening inside a function, it's good to have an overview of the whole module. So it's a good thing to collapse everything such that all the functions in here are collapsed. Then you can see, okay, what's imported? We're importing the NumPy, and we're importing the optimize from SciPy. And then there are a number of functions that are defined here. We already saw the value of choice function, and we can see that there's also a utility function which takes the inputs of both consumption and labor supply and some parameters and probably calculates utility. We can see here that is utility of consumption and labor supply decisions. That makes sense. We can also see that it's a way that once we have the labor supply, we know the implied C, so we can calculate that. So we have a function for that. And when we load labor supply, we also have the implied tax, so we can calculate that. So let's try to dig into this. So what's happening in the value of labor supply, value of choice, sorry. You can see that it's actually using the implied C function to calculate consumption, and then it's returning the utility value from the consumption and the labor supply choice. And of course, it's always given all these parameters. So if we do dig into that, then we can see the utility. That's just the formula for the utility that we had in the notebook. The log of consumption minus the new times this expression for the disutility of labor. And then we have the implied C, which is basically just a calculation of the X, the cash in hand plus the wage income minus the taxes, which now uses the implied taxes function. So we can go into that, which is the formulation of the tax system from the notebook, the base tax times the labor income plus the tax on the top bracket of labor income above this cutoff kappa. So in this way, we have now dig through all of these functions and sort of have an idea of what they are doing. If this went a bit too quick for you, just pause the video and try to look at these functions yourself and see how they are calling each other and what they're doing, so you have an overview of that. but let's return to the notebook otherwise. So we have called the function, so we have found the solutions. But one thing that's a good thing to think about here is, what about the order of the arguments? It's clear that we need all the arguments to find the optimal choice, because they all affect the choice in one way or another. But why in this exact order? Could this order be different? Or would that be a problem? Try to think about that for a minute. So we could not change this order around, right? If we would get the wrong result, if I changed around this, that would just be wrong, because now the function in here would getting the wrong argument. So I would use tau 1 for tau 0 and tau 0 for tau 1. So that just doesn't work. So it's important to keep the right order of the arguments. That in general shows that it's a problem with long lists of arguments, because you can easily make mistakes in that. So that should be avoided if we can. So this is something that's a bit bad about the implementation here. It's very simple because it just states all the parameters and then puts them in. But it means that we have to have the right order of these things. We cannot mess that up. One thing that sort of helps by doing that is to keep the order the same. So we can see here that this order is exactly the same as the order that we have down here. So sort of keeping the order fixed helps by that, but sometimes you will still mess it up, so really be aware of this. But okay, let's have a look at the results. So we had to plot the labor supply and the consumption choice against the wages. So let's do that. And this is exactly what we get out. We can see that the labor supply is generally increasing. In the wage, you want to work more if the wage is higher, except in this interval here, where we can see that actually labor supply is decreasing when the wage is increasing. And if we look over to the consumption choice, you can see that that's a point where the consumption is exactly flat. So you can show, if you dig a bit more into this, that this is because this is exactly at the cutoff. You don't want to sort of increase your labor supply when your wage increases, because then you would get to pay the top tax, and you want to avoid that. So just reduce your labor supply to keep your labor income constant, and therefore your consumption will always also be constant. So this shows it's rather easy to get such a result out of our numerical solution, which would have taken a bit more sort of work if you wanted to show something similar in analytical terms. Okay, for the final question, we needed to calculate the tax revenue, and a smart small trick we can use is that we can use that an equally spaced vector approximate the uniform distribution. So if we have an equally spaced vector, then it's exactly like we're just putting out the 1,000 individuals between the lowest and the highest wage point, which is exactly how a uniform distribution looks like. So we can actually just take the sum of the implied tax of the optimal labor supply for the wages. And then we can sum that up, and then we get the total tax revenue. And this looks like this. We could also have used random sampling. So we could have said, okay, let's set some seeds so that we can reproduce the results. Let us run 50 replications, because now the result will change for each straw. Let's save a vector of the total tax revenues for each repetition. Let's go through the repetitions. Each time we draw a new distribution of wages, we use the uniform distribution between 0.5 and 1.5. We set in 1,000 individuals, the n here. Then we allocate some space for finding the optimal labor supply, and we call this find optimal labor supply function for this value of the wage. Then we find the tax revenue just as we did before by summing up across individuals, and then we print the tax revenue if for the first 10 repetitions and for each 10th repetition after that. And finally we will plot the mean, and we will plot the minimum and the maximum value. So let's try that. You can see we get something that is in the ballpark of what we got up here. It takes a bit longer, and it jumps a bit up and down. Let's just wait for it to finish. I set in 50, so now it's finishing, and it gets something that's close to, but not exactly, and you can see that it has some span up here. So it's good that they give approximately the same results. If we increase the number of repetitions, we'll probably get something that's very similar. But this, of course, here up here was much faster and didn't need sort of any of the problems with repetitions and so on. But it's always good to think about different ways to solve the problem and show that they get you at least approximately the same result. That makes you more confident that you've actually found the right solution. Okay, finally, sort of an open question to end this notebook. What determines the tax revenue? You should spend some time trying to change parameters, change tax parameters, preference parameters, initial resources, maybe change the utility function, maybe change the distribution of wages, for example, to a log normal or a Pareto, and see how does that affect the tax revenue. That's a good way to gain intuition for how this model works. Let me just show you one thing that might be interesting. We can say, okay, what would happen in this model if we increased the top income tax? So let's start from what we had in point 1, and then let's just increase it to various higher levels up here. And now let's say, okay, we want to do basically the same thing that we did before, so we can use the code that we had. So we can copy in our code for the optimal labor supply here. We can copy in this. And we can copy in our line for the total tax revenue, and we also plot in what we have for the printing. So that's fine. Now I also want to remember what the tau is, so let me instead do it like this. Okay, so let's see if I did everything right. And now we can see, oh, I did something wrong here, right? I did write tau, so let's like type 1 instead. So now we can see that, okay, we start by this tax revenue, and actually we get a smaller tax revenue if we increase tau 1. So that was sort of interesting. Could we perhaps get a larger tax revenue if we decreased it? We could actually get a slightly larger tax revenue. But if we go very low, then the tax revenue is falling again. So there's sort of limits here on how big we can get the tax revenue. Of course, that will change with the other preference parameters and the distribution of wages and so on. So that's something that could be interesting to investigate. Thank you for today.